Так, слышно меня?
Если что, мы пошли в другой слот, потому что наш слот занят, и там просто чтобы не было проблем. Вот, поэтому сейчас...
Сейчас я...
Да, все, мы в церковь пошли.
Все, я веду теорию категории, ура.
Да, все, есть.
So, today we can start our lecture about category theory, and I want to start from some reminder. We have some notation for start. If you see Q sub modulo Q sub plus is just a maximum from 1 and modulo of Q. It's just useful notation, and of course something, the P of Q is just a product of coordinates of vector Q, and P plus is just the same but the product of Q plus. So P plus of Q is not 0. So, and I want to start from definition. We will call some number, some vector from Rn, very well approximable. I will write the same, VWA, if and only if there are infinitely many solutions, P and Q. This is as element interpreted as, you can think about it as about element of Zn plus 1. So, if such an inequality has infinitely many solutions. At last lecture, I said something else. I said something else. I said, I write here all the inequality. I write Q times alpha Q. Sorry, max Q alpha sub E minus PE is E from 1 to N less than 1 Q raised to the 1 plus epsilon over N. At last lecture, I wrote this inequality, but these two statements are equivalent. It's called a Hessian transference principle. This inequality has infinitely many solutions, if and only if this inequality has infinitely many solutions. But I will use this inequality. I think this is more comfortable for thinking about it, because it's just a simultaneous approximations. But it's more convenient for this branch of math. So. And we give one more definition. We will call some number A is very well multiplicative approximable if and only if we have infinitely many solutions of such an inequality. You can hear this just a maximum of coordinates. It's just a maximum of coordinates of vector Q. This is a multiplication of all coordinates of vector Q except 0 coordinates. But you can see that this is less than that. So we can have an multiplicative inequality. We can have some number such that alpha is very well approximable, but not very well multiplicative approximable. So it's more stronger statement. And one more definition. We have one has a open set in RD, and one has a embedding of this set to Ln. Is this L smooth embedding? And we want to consider approximation of points on this manifold. We will call image of this embedding M. This is just image of such embedding. It's just some manifold with dimension D in R times N. For instance, some sphere or something else. or Veronese cube if it's more comfortable for you. So, and I want to define very well approximable points on manifold. It's well-known fact that the measure of all very well approximable points in Rn is just 0. It's the corollary from Hinch's theorem. But I want to discuss more hard question, a measure of very well approximable points on some manifold. What it means? So let's write definition. Suppose that we have manifold M and we have some point on this manifold. And I want to write such an inequality so. But now I want to think that Q is not random points. Q is some point on manifold. It's point of manifold. It is not a random point. It's just a point on manifold. And I want, and such an equality has infinitely many solutions. Infinitely many solutions. And the same definition for very well multiplicative approximable points on manifold. So on manifold M. Manifold M. If yes, F of
G это очень хорошо приближаемое на многообразие.
Да, ну то есть, давайте так, давайте я уберу Y, давайте как бы, ну геометрически давайте посмотрим. Вот, например, вот есть у нас сфера, которая нарисована ужасно. Да, конечно, у меня почерк ужасный, прошу прощения. В общем, ну, как бы, ну, геометрически, вот есть у вас сфера в РМ, да, какая-то. Вот вы берете ее точку, и вы смотрите не то, как ее можно приблизить от в целом пространстве, а именно точками сферы. Вообще никто не гарантирует вам, что на каком-то многообразии есть рациональные координаты. Вот если вы возьмете там типичным многообразием, можно брать какую-нибудь хорошую эллиптическую кривую, то, что на эллиптических кривых существуют рациональные точки, там это вопросы открытые для каких. No, pp is some integer. It is not interesting for us because p is just some integer. It is not interesting. Yes. So, and I will prove theorem. One more definition. Suppose that we have y is some point of u. We will say that y is not degenerate point, or sorry, non-degenerate point. Non-degenerate point if span of what it means. We have one has manifold and one has the local coordinates f on this manifold, and we can consider all partial derivatives of such local coordinates, and we can consider linear combinations of these derivatives with order less than L. And if it gives us all space, we will call this point is non-degenerate. So, and I will prove such theorem. On notation, we have on manifold M, we can consider some measure on U. One has Lebesgue measure on U, So we can consider the measure on M as a measure on U. So if almost all in sense of measure on U, if almost all points of U is non-degenerate, then almost all points y belonging to U is not very well multiplicative approximable. That's Klein-Bock-Margulis theorem. So, at previous lecture, I prove that point is, if some point is very well multiplicative approximable, then it has some properties. So, we can consider lattice, such lattice. It's P plus Q f of y Q1 Qn. It's some lattice belonging to the space of lattices in L times n plus 1. So we can consider such lattice. It's some point from U. And we can consider the flow of this lattice in the space of lattices. GT is something like geodesic flow. It's e to the t, e to the minus t1, e to the minus tn, where sum of tk from k equals 1 to infinity to n is just t. So we can consider such flow gt of, and
everything is local inside you, not on the whole map. Yeah?
What? Sorry?
Все локально происходит в некотором открытом множестве U,
Да.
что на многообразии вы не видите.
Ну, у нас же как бы, я вообще все сформулировал тут в терминах множество U, если угодно, не хочу, ну, вообще у нас получилось такое нехорошее многообразие, ну, как бы почти с одной картой, у нас же вот есть вложение, но он такой неинтересный, казалось бы, многообразие, но ну, я все сформулировал во внутренних терминах. Ну, конечно, тут бы можно было бы говорить про внешние точки, про точки на многообразие, но я все перевел в локальные координаты, но это тот же смысл сохранило. То есть я взял точку конкретную, лежащую в U, построил по ней решетку, запустил по ней динамику, изучаю ее. То есть все корректно тут определено локально, да, и Y это, конечно же, ну давайте я напишу, что Y это точка, где-нибудь напишу, что Y принадлежит U. Y is point from U. So, and at previous lecture, I proved that if point very well multiplicative approximable, then the trajectory of such flow is unbounded. So, what was proved at previous lecture? So, I think this definition. So, it was proved before that one more definition. Yeah. Suppose that lambda is some lattice. Delta of lambda is just is shortest vectors of is just a shortest vector in Oh, sorry. It's not interesting. It's just the shortest vector in our lattice. It's just standard norm in Rn. So it was proved that lemma 1 is just a reminder, nothing new. Sorry, one moment. Let alpha be a very well approximable point. So one important notation: if some point is very well approximable on some manifold, it is very well approximable in all space also. But not on the other hand. If point is very well approximable in all space, it is not very well approximable on some manifold. But if it's very well approximable on manifold, it's very well approximable in all space. So if we have some very well approximable point, very well multiplicative approximable point, sorry, then we have such inequality. Sorry, one more time. We have an arbitrary epsilon is greater than 0, and some p q. From this definition, it's some solve of inequality solution of something like that, but for very well approximable points, multiplicative approximable points. So I think I should write there the inequality for very well multiplicative approximable points, because it's something important for us. So oh no, that's so this is for very well multiplicative approximation points. Sorry, it was a mistake before, but now this is a definition of inequality for very well multiplicative approximable points, because we have p plus there. Sorry. So if we have some point, we have a solution of this point. We have a solution of such inequality. So what we have then? Then we have such inequality. R is just something miserable, I think. It's just plus raised to the power minus epsilon over n plus 1. So we have such numbers. And t sub e is an logarithm of qy plus over r. So, and gt is just e raised to the t minus t1 minus tn. So then we have it was proved in previous lecture. It's some technical and miserable statement. What it say? If we have very well multiplicative approximable point, then the trajectory of geodesic flow is unbounded. It's unbounded because what it means to be unbounded in lattice space. It means that from Euler criteria that we have very short vectors, as small as it possible. So now we have some miserable statement, and I want to, yes.
Извините, у нас R это получается произведение куитых плюс.
Да, да. Ну да, но оно, видите, это же какое-то число, вот кушки, это число большое, куитых. Вот, я его, конечно, в маленькую степень вложу, но я его делю, то есть это какое-то довольно маленькое число, но вот мы сейчас, вот это такое техническое утверждение, я сейчас из него выну уже приемлемое утверждение, с которым можно работать, потому что с этим, конечно, работать нельзя. Corollary. We have a corollary. This is useless now. So, corollary. We can suppose that y is a very well multiplicative approximable point is, so alpha is some very well multiplicative approximable point. Then we know that there is some gamma is greater than 0 such that exist infinitely many t belonging to that n plus such that delta of gt lambda y is just less than e gamma t where gt is just an e raised to the t minus time
То есть, когда мы пишем гамма-Т, мы подразумеваем, что это у нас первый координат.
Yes. If you see bar, this is a vector. If I don't write bar, this is a number or this is a mistake. So we will put this corollary because it's more convenient and it has more sense because we know that, sorry, minus, obvious minus. So it means if this has some dynamic sense, that trajectory over the action of flow is unbounded due to Euler compactness criteria. Sorry, one note. Does everybody remember the Euler compactness criteria? No. Oh? I don't remember. Oh, so I need to write the Euler compactness criteria because it is not obvious what it means to be unbounded in lattice space. Because it's theorem, it's Euler. I think, suppose we have some k subset of omega is just a space of lattices. Sorry. It's space of lattices, and we have some subset. K is unbounded. So it isn't good. K is close we have some closed subspace, so K is compact if and only if there is epsilon greater than 0 such that K for all lattices belonging to our family of lattices, the length of shortest vector in this family is greater than epsilon, greater or equal. So when I say that some flow is unbounded, I mean there is no compact such that all trajectory belongs to this compact. So for all compact, we will escape from this compact at some time. And from this inequality, we know that our trajectory is not belonging to some compact. It's unbounded. It's what I mean when I say something about unbounded, to be unbounded in lattice space. Is it clear? It is not proof, it is just some statement. So now we can prove this corollary because it's it will some dynamic in homogeneous spaces, so it's something that we want to study. So our proof. So so it was said before that R is just product of Q raised to the minus epsilon n plus 1. So it can be rewritten in some sense. We know that T sub y is just logarithm of Q sub E plus over R. So E raised to the Ty minus Ty is just R over some QE plus. So then QE plus is just R times E Ty. So R is just so product of Q plus is just R and E raised to the sum of T sub y, but sum of T sub y is just E to the T. So so what I want to write here. So I want to think about R as about E raised to the minus gamma T. Yes, of course.
Такое подозрение, что у нас, кажется, произведение...
Oh, so sorry, raised to the n power, raised to the n. We have n multiples here, and we have such equality, because what it means? It means product from E equals 1 to the n, QE plus, raised to the minus n plus 1. So we have n here, because due to this quality. So we know that, and I want to calculate some gamma such that R is just E raised to the minus gamma T. E is just R is just E raised to the minus gamma T. So I claim that gamma is just epsilon n plus 1 plus n epsilon. How we can prove that fact? Well, I think it's obvious. Why? Because we have such an equality, such quality, so we can raise it to the power minus e over n plus 1, p plus q, raise it to the power minus epsilon over n plus 1 equals r minus epsilon n plus 1 and e to the minus epsilon t over n plus 1. But we know from definition that this is r. So, это доску видно в камеру?
Да.
Хорошо. So, let's rewrite it. R raised to the 1 plus epsilon n plus 1 is just e raised to the minus et n plus 1. So R is just minus et n plus 1 over 1 plus epsilon over n plus 1. So you can calculate it, and I think it wasn't a mistake to think that we can think that gamma is that. So I hope that was correct calculation. So now we can think that this just e raised to the minus gamma t, where gamma is constant epsilon over n plus 1 plus n times epsilon. So, but we know from theorem, from lemma 1, we know that delta of gt lambda y is just less than r. But it's just e raised to the minus gamma t. So we can consider, but this t is not integer points. T is some miserable points. It's obvious irrational and transcendence, but as I said something about integer points, the element of z plus n plus 1. So,
Можно вопрос? Откуда у нас n epsilon взялось?
что? Ну вот раскройте скобки.
Умножим на n плюс 1, получим там n плюс 1 плюс 1.
Ну вот когда у вас n плюс 1 пойдет в знаменатель, вот здесь.
У нас сверху получается эпсилон t,
Ну,
снизу n плюс 1 плюс эпсилон.
ну сейчас, может быть, я ошибся при расчетах, но важен не конкретный вид гаммы, важно, что это какое-то положительное число, которое зависит только от n и эпсилон. Может быть, я говорю, я ошибся в расчетах, это не важно. Вообще, ну или Маргулис, к слову, Маргулис с Клейнбоком такая же константа, это не важно, какая она. Важно, что это положительная константа, которая не зависит от t, зависит только от эпсилона и от n. То есть вот у нас есть такая константа, которую мы можем прям явно посчитать. So, now we have some constant, it's incorrect maybe, but it is not interesting because this constant depends only on epsilon and n. So, sorry. This is from lemma 1. But we can consider some point, it was stated before that we can consider only integer points. So it's some exercise. There is some gamma bar such that delta of gt of lambda y is just less than e raised to the minus gamma bar t, where t is just vectors from the floor. It's just integer parts of numbers. It is a very hard exercise, but it's a little bit technical. So, is it clear statement? I think it's kind of obvious. Because it's very simple, so ну, так, ну, согласны в это поверить или надо доказать? Мне кажется, что это очевидно, что я могу здесь вот взять целую часть навесить и не сильно испортить это гамма. Ну, чуть-чуть его мне придется увеличить, но не сильно, потому что если вы посмотрите на разницу, здесь вот просто вместо t надо поставить разницу, ну, дробной части и увидеть, что мы длину вектора-то не сильно портим. Ну, что-то мы вектор укорачиваем, но как-то не сильно, ну, не страшно. Главное, что контролируемо, там экспоненты только в степенях, там, ну минус единичка, ну что, ну немножко укоротим вектор, не беда же. У нас же асимптотические оценки. So it's kind of obvious as exercise. Why? Because we can rewrite it in such sense, because it's just gt lambda y, its worth is just delta gt minus t times gt. But what it means? G over t minus t is just e but this is so close to identic matrix, so the length of the delta of this lattice and delta of this lattice is so close, because this matrix is so close to the identic matrix. So it is not rigorous proof, of course, but it's kind of rigorous. It's almost rigorous. So now one technical statement to finish our proof. And one question: does everybody know Cantelli's theorem? But there is some famous theorem from probability theory or measure theory, which called Borel-Cantelli's theorem. It's a well-known fact, or I need to, or I should to remind this statement. So one more reminder: it's Borel-Cantelli theorem. Borel-Cantelli theorem. Borel. I didn't know how to write Cantelli, so I didn't write it. So we have some measurable space, so it's X. There's just space, it's sigma algebra, this measure on this space, and we have some family of sets belonging to sigma algebra. Sigma algebra, it's measurable sets, and suppose that the such series converge. Then, not P, the measure, it is not probability theory. Hence, measure of such set is just 0. Not probability, measure is just 0. It's first Borel-Cantelli theorem. There are two Borel-Cantelli theorem. What it states: one has some measurable sets, n from 1 to infinity. And we know that the sum of measures is finite. So we can consider points such that every point belong to the infinitely many sets. So this is just set can be described as such set. This x belonging to x capital, so we can rewrite it. It's such that it's all x belonging to the x capital such that exist infinitely many numbers n such that x belongs to the an. So it just points such belongings to the infinitely many sets an. Something like that we consider because we want to find infinitely many solutions. So of some inequality, so we will write some sets like that. And we will prove that some series like that converges. So the measure of, we will prove that the sets of very well approximable points is the same set, same of this type. So now one technical statement, sorry, one technical statement. I think it should be called proposition, not lemma. It's very hard statement, so it will be proposition. 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 So suppose that f is L smooth embedding from Rd to Rn and almost all points of U are.
What is the index of
is L smooth embedding. CN. So it's so if almost all points of U, so U, if almost points of U are non-degenerate, then exists some B ball. B is subset of U. Not almost all points. Sorry. Suppose that X belonging to the U is non-degenerate. So we have some point. One has some point which is not degenerate. So there is some ball and there is constant D and rho greater than 0 such that for all T, measure of X belonging to the ball such that delta of GT of lambda f of x0 is just less, is less than e raised minus gamma, minus epsilon is less than d epsilon over rho raised to the 1 over dl measure of B. It's some technical statements. I will not prove it because it's very hard. But we can consider some corollaries from this proposition. So, corollary. So, we can consider not random epsilon, not arbitrary epsilon, but our epsilon from theorem about very well multiplicative approximable points. So, we can rewrite it for epsilon e raised to the minus gamma t. So, measure of points of x belonging to the B such that is less than e minus gamma t is less than d e raised to the minus gamma t over dA over rho raised to the 1 over dL and measure of both. So, we want to prove that the measure of very well multiplicative approximable points on some manifold is 0. But we know that every manifold is second countable. And due to this fact, it's sufficient to prove that for some ball, that for almost all points, there is some ball with center at this point, such that measure of very well multiplicative approximable points in this ball is just 0. Is it clear? Молчание повисло. Ну, еще раз давайте по-русски повторю, может, на английском было слишком плохо. Смотрите, у нас есть многообразие, оно имеет счетную базу. Вот мы хотим доказать, что из нужных нам точек их мера 0. Мы вместо этого докажем такое более простое утверждение. Мы возьмем почти любую точку, окружим ее шаром, и посмотрим на меру тех хорошо приближаемых точек внутри этого шара. Вот если она 0 для такого каждого шарика, то мы и доказали из наличия счетной базы, это как раз следует, что у нас на всем многообразии таких точек тоже нету почти что.
А что значит для каждого такого?
Что значит для
У каждой точки есть...
Ну, почти у каждой.
Почти у каждой точки есть круглая окрестность,
в которой нету хорошо приближаемых. Да, существует. Ну, не каждая, но какая-то. Но дальше мы пользуемся счетностью базы. Говорим, ну, если надо, возьмем даже шарик поменьше, сделаем из этого счетную базу, но какие-то точки мы не покрыли, но их мера 0, их не страшно, да? А все остальное мы покрыли, и там мера 0. Ну, а дальше уж, извините, счетная аддитивность меры. Все. Поэтому it's sufficient to prove that for almost all points one has some ball in which measure of very well multiplicative approximable points is just in a 0. So we know such inequality for measures. So let's use this fact. So I need to raise something. So, but it's just for almost, it's just for all t, is for all numbers, but we can consider only integer numbers from the previous lemma. And we know that we can sum from other t But from this inequality, we know that this is just less than infinity. That this series converges, and so it means from Borel-Cantelli theorem that the intersection from one to the of unions so is just so we know that the measure of such set is just 0. But it was proved before that very well multiplicative approximable points is subset of such set. So the measure of very well multiplicative approximable points is just a 0. I want to note that is not obvious statements. It's the most it's the hardest statement from the paper of Margulis and Claybach, and they use a lot of definition and hard theorem to prove it, but I has not enough time to prove it. If you're interested, you can find the issue of Kleinbach and Margulis and read the proof of this theorem. It's so hard, but I think we can stop here.
Okay, thank you very much for such a detailed knowledge presentation. It was very cool. Do you have any questions? If not, maybe we can make a break. Then we will proceed with Anya's talk on a very different topic. Now we understand well how dynamics is related with number theory, thanks to this last work. And it will be a moment to learn a little bit how dynamics can be connected to analysis and some tools from probability theory analysis. So let's make a break.
Страшная правда состоит в том, что я только разобрался в доказательствах. Я был готов достаточно интересно делать.
Подожди, а мне прикрепить?
Смотри, микрофон так, чтобы было слышно, где-нибудь на воздухе. Ну, что
Ага.
вообще,
А это просто куда угодно.
Это скобу как раз, чтобы на карман, например, повесить. Только аккуратно.
Ага, ничего не сломать. Поняла. Ничего не отключить.
Да, смотри, только аккуратно, смотри, чтобы не отходило по штеке.
Ага, поняла.
Что должно быть?
Спасибо. Можно начинать тогда? Мгм. So today I wanted to tell you about transfer operator method, and the article I saw starts with very general idea that if we have a glass with the center, that is the function f and measure nu. If we do something like shaking, then we have it more steep, and it looks like the head f measure. And the idea is that we want to, we can. I wanted to show the general idea that if we have a glass of sand and shake it, then it becomes steep, and we can't say what happens with one piece of sand, but we may say what happens with all. So it was a general idea of the article, and now I want to provide some notions. So the transfer operator, I think it's not good I spent all board here. So the transfer operator T, that's like of, not like that, of a dynamical system. System T is T hat of the action T on mass nu. That's like the action of T to F the mu is equal to T hat transfer operator there, and it's like F the nu, and the new mass is T hat F. And so if the basic notion of it, what we need a minimal setup.
Sorry, what is T hat? It's forgetfulness.
It's operator.
So is it f of t? Or it's some operator?
Yeah, it's the operator T hat applied to function f. So with
F of t, does it suppose that t is a measure preserving?
yeah, we want to ask so.
Oh, thank you.
So a minimal setup is we have a space X, measure nu, system T, and measure sets F. And so what we want to ask? We want to ask that T hat that from X to X is non-singular. By that we mean that if we apply T minus 1 to nu, it would be absolutely continuous in terms of nu. It means, I will write it more precisely, it means that for all measurable sets, if the measure of the set is equal to 0, then it follows that the measure of T minus 1 is equal to 0. That's what we ask mostly. Now without heads. And so we want to know if we apply to F our operator, what would be the mass landed on the set E, measurable set E. So we write on E. So we want to know the measure of x in x, that is in E. And we, yeah?
T is measure preserved or not?
Not really. We want it to be absolutely continuous.
So.
Yeah. Yeah, sorry, I said not like that. So we want to know where would go f nu. We say it is nu f by definition, and so we write down it as an integral of identical and t measure, and now we write it as put t here. T minus 1. And so the next step is to use Radon-Nikodym derivative. That's like we write it again as not like that. And so we are ready to say that that thing is transfer operator. So I write it to look a little bit better. So
maybe
yeah.
Apply not to phi, but not to f, but to some concrete function, because it is an indicator function.
Yeah, that's indicator function.
So f, sorry, a moment please, because we have an indicator here, so we want to write t cap of f, so we need to rewrite it as some. Давайте на русском сформулировать, а на русском это звучит плоховато. Что у нас вот когда оператор, вот так что мы подействовали, что у нас осталось только t с крышечкой от f до μ, да? А у нас тут остается еще и индикатор остается. Сейчас. Оно так и должно быть, просто или как? Просто непонятно, вот, как бы, оператор переноса к чему применить? Какой функции?
К функции f. Мы вот хотим функцию f, которая...
Здесь в конкретном случае функция. Нет никакой функции f абстрактно. У нас есть индикатор. Но если мы к нему применили, не должен ли индикатор, если вот это производное Радон-Никодима, чтобы это было определено, как-то еще понятно. То есть у вас слева функция f есть, а справа нет определения.
Да, но она вот здесь появляется из-за nu_f, потому что у нас nu_f это, можно сказать, что интеграл. Сейчас скажу поточнее.
Да. У вас мера.
Просто μ.
Да. А просто стоит f от d. F d.
Вон она там сидит.
Вот
Да, все, тогда согласен.
Да, the nu by e. But this definition isn't convenient, so in general we will use the characterization. I'll write it down now. So we use the characterization. I'll write it as proposition 1. The characterization of transfer operator is that for all phi that integrable, we can write the composition T hat F, the new is equal to phi composition T, and now multiply on F the new. So the first thing we are going to check is that in case of our definition, this equation really holds. So what we are going to say, we take phi and write down let's take T hat F here. And now let's do the same trick. Of putting T inverse here. And so now we can change it like composition. And now let's just put that new index phi is equal to f the new. So we will get what we wanted. F the new. So we have proved that it really holds, and now we want to check why here it is characterized. So let's do by the contradiction. Let's suppose there exists two functions such that the things really holds. We can write down, I think L1 it's here, so we can write down it holds GE, the new.
So G belongs to the
L1.
L1.
Yeah. And it will hold for E in y is equal to 1 and 2. Then we say that it happens for all phi. So let us take phi is equal to sine g1 minus g2. And so if we put it here, we know that 0 is equal to phi g1 minus g2. And it is equal to just the absolute value.
Sorry, but why this is a 0?
Since we know that they are equal to Z1. Not I think better to this one we take.
So and why this is a 0?
So we say that G1 the new is equal to composition T F the new, and with G2 is equal to phi composition T F the new. And so I have lost space. And that is why we know that if
It's maybe not T, but maybe not phi, but G sub E. What you write here, phi composition T composition F, but sorry, to tau.
yeah, I see.
Because you write something.
Yeah, I see. I'm not right. Mm-hmm.
And why is this?
Yeah, I have written not correct.
What's wrong?
I found I have written not correct in the equation and don't have the problems with equal to 0 of sine g1 minus g2. I think it should be like that here, like that, and so. Mm-hmm. Yes. Honestly, I don't think I have now a question, an answer why it should be 0, as I have written not correct here. Mm-hmm. I don't think I have a short answer. I have written.
Okay, you go ahead and
Yeah.
then we will try to fix it.
Yeah.
Just to give the general idea, the key point is that
Yeah,
that talk is very
that's now is
introductory.
question.
Part. So
Yeah, so we have g1 minus g2 is equal to 0, and here, so we wanted to say that then g1 is equal to g2, and that's it. So what we wanted to say is that we can use such characterization that if this equation holds, then it's transfer operator.
I think now how we can claim to this conclusion. We can suppose that this operator is not a unique operator such that from all operators holds to this condition. So we can consider two functions, g1 and g2, such that we have as a values of this operator, t of g1 and t of g2. And and the difference between two integrals is just 0, because we know this is the same function. T of g1 is just t of g2. So, сейчас. Нет, даже ладно, это не очень аккуратно. То есть, нет, ладно, я ошибся. То есть, когда что-то в таком духе, мы хотим предположить, что есть два разных оператора,
Да.
с таким свойством, но оператор однозначно определен своим действием на любую функцию. Можно что-то выяснить, ну ладно, так быстро не чинится.
Да, я тут неправильно написала, извиняюсь за это. So now let's see an example how this characterization can be used. So the first example is Gauss map. So we have T from this to this. This the formula, and nu is just a Lebesgue measure. And so we know that it looks something like so it looks something like that, and we want to show how we calculated t hat with the help of this characterization equation. So we write that for all functions that's true that the integral t hat f of the x is equal to same integral but the composition. So we just write the characterization here, and now we want to calculate the following. So if we look at the picture, we can rewrite it as the sum when a is equal to 1 to infinity of the integrals phi minus 1 x, and where we take from 1. So we can change variables. That would be new increment, and so x is equal to 1 divided by plus e, and so we write it. The limits are changed like that, and the integral is in the following formula. Here I don't have enough space, so it wouldn't be beautiful enough. It's minus. So we just simplify this a bit. We take this minus to change limits. And the following sum. Sorry, it looks bad. I have already done it. Here is so now we are done, and we can see here the equation looks like that. So we have t hat f here, here. So by this example, we know that t hat f is equal to the sum of 1 divided times and the fraction. So it was example how we can use the characterization equation to find the t hat. And now I think whether I want to do one more example about doubling. I think not. It's mostly the same as here. We just apply characterization equation and write it, and so we know the form of t hat f. Now I think I'll write some properties.
Do you plan to cover also some applications of this technique, like you tell what transfer operator is and then mention maybe where is it used or which kind of problems, or it's not included?
Not really. I wanted to say how we can use the transfer operator to know something about initial T, but only a little in the end.
Okay, but
Yeah.
then I will comment briefly what
Uh-huh.
you are raising, just that why it exists. The key point where we apply it very directly is the situation where we need to construct an invariant measure. Very often we are not given some natural invariant measure. I mean, in many examples we saw, we understood how it should look like. It was the Lebesgue measure or some version of it, but it's not always the case, of course. Because in plenty of natural questions and dynamical systems, you can be missing the natural invariant measure, but you want to construct it. And one of the most efficient and standard approaches is somehow, it's called dynamical formalism, and it can be related to some structures from statistical mechanics, but you don't need to think much about it. What I want to say is that just simply the invariant measure may appear as an eigenfunction of the transfer operator with the sum eigenvalue. And so the key reason why people started to study them was to construct invariant measures.
So I'm going to list some properties. The first one is that the operator T hat is positive and bounded. And also its norm is equal to 1. Positive linear operator. Also it's bounded. And also its norm is equal to 1. So now I'm going to prove it. The proof that its linear operator is going to be quite straightforward. We just check the linearity.
Значит, я правильно понимаю, что можно понимать этот оператор примерно так, что вот у нас есть какая-то динамика, и мы хотим вот интегрировать функции, и вместо того, чтобы интегрировать функции вот на каких-то траекториях этой динамики, будем интегрировать функции как раньше, но менять плотность. И вот то, как меняется эта плотность, это и есть вот этот оператор вот это и есть оператор тест-крышечка. Или как? Можете еще что-то характеристическое свойство написать?
Ага, ну вот это характеристическое свойство, оно скорее, мне кажется, для вычисления, про то, что и тут дню.
Они просто эффективны.
Сейчас помню, в каком порядке шли. Мне кажется, что так.
Нет.
Да, сейчас. Нет, зависит от крышечки. Сейчас помню, в какую сторону тут шли. Так, фи. Давайте так, чуть-чуть поправим. Финти с крышечкой F. Ага, а тут композицию берем, да, вот так.
Ну да, то есть получается, как бы мы берем функцию на какой-то траектории, то есть поменяли, и вместо того, чтобы ее интегрировать, мы интегрируем старую функцию на по новой мере.
Да.
Это понятно.
So now we want to check that its linear operator. We will do it quite straightforward. Just check the linearity. Lost it. So we will do straightforward, as I said. Just also by characterization equation we will do it. Alpha f plus beta g by new. Also characterization now. Alpha f plus beta g. Now we will just remove the brackets. It would be like and plus b. And now we will do characterization equation one more time. Now put t hat. The same with b. And now also put it together as at the beginning. So now we end and we see that t hat alpha f plus beta g is equal to alpha t hat f plus beta t hat g, as we wanted. So we checked the linearity, just applied the characterization equation as here 2 times and that's it. Now we want to check that it's positive. Yeah. Positive means that if we take f that is non-negative almost everywhere, then we get that t hat f also is non-negative almost everywhere. So how we will do it? Let us consider the integral t hat f du by where it is positive. So as it is positive, we know that not where it is negative. So where it is negative, we know that it's less or equal than 0. And now we want to show that it's at the same time more than 0, so we will get that it's equal to 0. So what we do here, apply identical less than 0. And then one more time characterization equation. That's in composition with our operator and f. And now let's see. This composition is more or 0. And this function f, as we supposed it's more than 0 almost everywhere, is also non-negative. So we see that this is non-negative. And by this line, so we see that this integral is equal to 0. So what we want to say by it is that t hat f is equal to 0 almost everywhere on the set t hat f is less than 0, and on the set when it is non-negative, it's of course non-negative. So by that we get that t hat f is non-negative, because on the negative side is equal to 0 almost everywhere. So now we get that it is positive. We checked that if f is non-negative almost everywhere, then t hat f is also non-negative almost everywhere. And now it's rest to check that it's bounded and its norm is equal to 1. I think I used all the blackboard again. Okay, so now let's check that it's bounded. So if we have f from integral, and so let's write down the norm. It's equal to the integral. And we can do the same trick we did with the sine function today. We can write its sine. And again TF. And now again characterization equation. So we have a composition of sine and TF here.
T. But why
Not
T?
here.
Maybe
Yeah.
just T?
Yeah, that's right. Thank you. The new here. And now we want to apply Hölder inequation. So we say that it's in L empty and F here. So we can write down of sine T F composition
T.
T. Thank you. And norm of F. But as its composition with sine, we know that its norm is 1, as it's the upper bound and it's sine. So it is equal to 1. And we get that is bounded by the norm of F. So what we get is that TF is more than F1. So we get here that the norm of T hat is not less than 1. And now we want to show that in fact it's equal to 1. So now we want to show that it's less or equal to 1, and then we will get that it's equal to 1. So how we'll do it? Maybe I'll over. I think I have some space here. Let's have F that is strictly positive. I'll write it like that, L plus. Then T hat F. Right, we'll write it again. But as we have shown, it's positive. So if F is positive, then it's also positive. So we can just not take the absolute value. Continue here. And also we can add here 1. Now one more time characterization equation. That is 1 and that is F. And as F positive, we get here F absolute value mu, and so it's equal to just the norm of F. So we got here that the norm of T hat is equal to 1, as we wanted. So looks like we have ended with this proposition and the second one. The second one I think is just for help to prove the third one. So so I'll write them together. The second one is that we can just keep t hat. That's written like that one. New is equal to f. And so the third one is that happens for all f. And so the third one is that for all f and for all phi, we get that t hat, and now again the composition with f is equal to phi hat f, almost everywhere. So now let's check the second one. I think the key idea is like that one. We'll just write once again the norm. T if is equal to f. And we can write it down as the absolute value. Continue. And so we just see two cases. If f is non-negative, then we get what we wanted. And if f is negative, then we also get what we wanted, just here is minus. That happens because we know the positiveness of t hat. We have shown that if f is non-negative, then t hat f is also non-negative. So here we can apply the same to minus f that is non-negative. And so taking these pluses, we get what we wanted. So this is just helpful for the third one. Let us check it. So let's check the third one. We also will do it just straightforward. Just check that here is f, the new is equal to t hat f, the new. And then we apply the characterization again. Or maybe not. Let's apply the second one. We have shown that here we can just not put t hat here. So apply 2, and we will get that decomposition f again is equal to phi t hat f. And then one more time characterization. And so that's what we wanted to get here. And I think that's all properties. And now I wanted to tell a little about the method. Этого, да? Второе, которое вот это.
Нет, в смысле третьего, потому что там у нас получилось просто, что пишет с крышкой F, да, слева и справа.
Да, и я вот это вот свойство тут применила, просто вот выкинула Т с крышкой, получается, вот это свойство выкидывает Т с крышкой, вот, и мы, получается, вот выкинули Т с крышкой, просто это переписали, композицию тут, а это оставили. А теперь применили characterization, который нам вот позволяет вот эту композицию поменять на умножение тут и с крышкой. Вот, и получилось как раз то, что мы хотели. Получается, мы правую часть никак не преобразовывали, а в левой вот применили второй пункт, который доказали, чтобы выкинуть Т с крышкой. Ага, получить такое вот равенство. So now I wanted to say here a little more about the method. The key point is that we know, if we know something about T hat, we can also say something about T. So I'll write some propositions again. So I think the first thing I will say is the construction of absolutely continuous invariant measure, invariant probability measure. The authors use the shortening by the first letters, that is R, A, C, I, F, P. So we also give two definitions now. One is more convenient and the second one is less. The first construction is so. Construction 1 is so. We have again non-negative h, and we know that it integrates to 1. And also the eigenvalue, it's eigenvector with eigenvalue 1. Like that. And then new h. That is by definition we hold h the new is that measure is absolutely continuous invariant probability measure, and that's all again not convenient, and we use the second construction. Construction 2. We say that if for some non-zero f, it holds the limit f converges to h f d mu. Weakly in L1, and then the measure that is the same write it better h the new is again absolutely a continuous invariant probability measure. I guess it's the same as we can see here that as, yeah.
Tn of f
T hat n f weakly converge to h integral f the mu.
What is h? Is some function?
Yeah, we want to check. The statement is that if for some f holds with some h, then the measure like h the mu is that absolutely continuous invariant probability measure. So we want to construct by h the measure. So it's to the same constructions. Here the positiveness of ash is also held by the fact that T hat is positive operator, so they are the same, but the second construction is again more convenient. And the proposition and the proposition is so. If T hat and F converges to ash integral f d mu, weakly and L1, I'll write weakly on the converge symbol. For some non-negative again. For some non-negative f not equal to 0, then T has again this absolutely continuous invariant probability measure, and ash is its density. So let's provide the proof here without loss of generality. Let's write that integral d mu is equal to 1. In another case, we can just use the normalization to obtain it.
But if integral f d mu is 0, how we can normalize it?
It's 1.
So you say
Yeah, we say it's not equal to 0.
Not equal to 0.
Yeah. So without loss of generality, it's equal to 1. And so let's write again characterization. Phi ash d mu is equal to, let's rewrite it as ash. So we have that T hat n f converges to ash as this integral is 1, and so we get that ash is a limit of T hat n f. So let's put it here. Limit e and here T hat n f d nu. We will use not n but n plus 1 to obtain the characterization again. So it's the limit of phi composition T hat, as we have put it like T hat n. D nu.
T and maybe.
Yeah, thank you.
T and f.
Forgot it here. And f d nu. And so let's again change it with the limit, as ash is the limit here. So we can say it's phi composition T ash d nu here. So we have checked that our new measure ash d nu is T invariant, and that's what we wanted to check.
Sorry, it's just phi of t.
Yeah, so we have that. So that's why here our new measure that is as
Is it, sorry, I don't understand why, how we came from first line to the second. Wow.
here.
No. This is first line. I said about second line without limit.
We have said that the limit of t hat n f is our h.
But this is a big limit. Yeah, I think you use this in some sense, but I don't understand how to use this. That's why this is a weak limit. To be weak limit, it means some sense in binary space. Был предел, вы его пустили, да?
Ну, собрали.
Он интеграл, потом перешел через эти.
Сейчас я был. Это же слабый был предел?
Да,
То есть
да.
Надо, наверное, как-то... Сейчас. Сначала у нас был предел интегралов, вот таких вот, для любой функции фи, да, он был просто потому, что это определение слабого предела, что это сходилось к f от ну, да, в принципе, понятно.
То есть там все правильно.
Да. Там просто n было нужно написать,
Это как раз то, про что я говорил, там как бы самой упрощенной версии, что вы видите эту меру как собственную функцию для трансфера плюс.
Только, мне кажется, неправильно написано. Вот тут не фи h d μ, а фи t h. То есть крышка.
Да.
И нет, тут это правильно.
Да.
Фи от t, фи от t h.
Слева.
Да.
H потеряла. Она тут.
Нет, это должно быть так, слева интеграл написано неправильно. Потому что там t есть. Там перед этим.
Нашла. Угу. Так. Она так. Вот этот так.
Не, вот в этой же строчке, это первый интеграл, до знака равно. Вы стерли, то есть два интеграла, то, что вы стерли, и то, что левее.
Вот это, да?
Да, тут t должно быть. Все-таки, да.
А тут же H была у нас.
И это, конечно, такой
Которая-
вопрос, но иначе это не то, что мы хотим доказать. Просто мы же хотим доказать,
Ну да,
функция
перепишем.
расходная мера, а это вариант.
Угу. And lastly, let's check the properties here about the correlation. The property is that an estimate, we'll not write it with letters, so if t hat n converges to integral f d nu, then for all phi, we get that the, I think, covariance n, and that is by definition, okay, we don't write it, by definition here is less than t hat n f minus integral f one, and again, so it gets us the rate of decay of the covariation that is like about the norm f minus integral f the new here, and we can consider it like the 0 time and the n time, and we know the rate of decay.
Sorry, what we state, we have some limit.
Yeah, we say that if t hat and f converges to f the new integral, then the covariance between f and the composition of Tn is decays with this rate.
It means, сейчас вот в скобочках это написано или нет?
Here, it's the rate of decay. It shows the speed or how the covariance falls. Decay.
Sorry, it's just big O. What means by big O? Is it composition of 0 or big O from analysis, or what it means?
No, I just wanted to say that it falls, decays with such speed. That's it. We'll also check it just by definition. So let's write Tn here. That is by definition is written like take it here by definition f phi composition Tn the new minus f the new again integral phi the new, just wrote it by definition, and now let's write it here. Write it here again. We just use that as a correlation.
Covariance is just a multiplication of
we use that one. So let's rewrite that again. The new minus integral f the new minus, not like that, yes, new, the new. Sorry, it's a bit messy. And the last step here, use the characterization again. Just put it together. And one more time, Hilbert inequality. Hilbert inequality. So again, it would be by norms and f minus f the new that one and that infinity, and so it ends the proof of this property that the covariance falls with such rate. At this point, I think I mentioned all properties I wanted to do. So looks like that's all.
Okay, do you have any questions? So it's the moment when you can see that some analytical and some probabilistic tools can be applied in dynamical systems. For example, the question of the decay of correlations is one of the central, not only in for some abstract dynamical systems, but for instance also for hyperbolic ones, people examine this kind of questions. And as you noticed, it's also rather efficient to construct invariant measures and then to examine their further mixing properties, the decay of correlations for the measures, and so on, to study the nature of the measure.
Suppose that we know something about eigenvectors of this operator. What we can say about its something about ergodicity or mixing property of T with respect to some invariant measure, for instance?
You mean the original? Yes. So it depends which measure do you take. But very often, very often, if you use transfer operator to construct the invariant measure, so this measure is a kind of eigenfunction up to some renormalization of the transfer operator, then you will get some ergodic properties automatically. For instance, if you apply the thermodynamical formalism to construct the invariant measure, then this measure is necessarily ergodic. It's just an automatic property. One needs to check it once.
So,
for which class of them?
Sorry, as far as I understand, you don't need to know anything about the eigenvectors, but about eigenvalues.
Yeah.
Specific vectors are...
Vectors are not needed, yes, but... yeah, but then you get many good properties automatically. It depends on the properties of the original transfer operator. But for instance, if you have some good properties like quasi-compactness and this kind of things, so you can guarantee that you do have some nice eigenvalues, then you can...
So, if one has some measure such that T of this measure is just this measure, so it's eigenvector with eigenvalue 1, then we know that this measure is ergodic. Yes?
Probably in the simplest case it should work like that. I have in mind more this more delicate situation, but for instance you can use a similar technique to prove ergodic theory for Markov chains. And then you will have ergodicity indeed. It will follow from basically Perron-Frobenius theorem. So it's some generalization of the same thing basically, as you studied in Markov chain theory. So, and it works well not only for random but also for deterministic system. If you can model them with Markov shifts, it works in the same way. Hopefully Dima Chibasov will give us a talk about symbolic dynamics, and then we can discuss it a little bit more. I will show you more explicit examples of these things. But it's a way how the pure analysis works, serves for dynamic properties. Да, можно, наверное, заканчивать. Спасибо большое, Аня, за доклад. Okay, so next week we meet online for one Zoom talk, and on May 7th we are free. Thank you, vacations.